Hello, everyone. That was so basically we are just 2 talks away from the end of this great conference, and we talked a lot about web applications. And now I suggest you to look at those from a little bit different perspective. How do I switch? Okay, that's short disclaimer. I will scratch the first surface of a very important and huge topic called system design. And apparently it's so big, I wouldn't even fit it if I would have 45 minutes instead of 15. But anyway, if you will be interested and can continue discussion, please consider to connect with me on the LinkedIn. I am always open to help. And before going further, I would like to introduce some theory and definition. So when I talk node, that means physical or logical unit of a cluster. And when I talk instance, it means running process of software component or basically your application. And RPS stands for request per second, which is one of the key components of the system design. And system design starts with capturing non-functional requirements. So basically the technical specification of your software, and is required for, the whole thing is required for making an informed decision about budgeting, capacity planning, and basically what your system is, how it should be designed. And performance benchmarking is one of the key techniques to actually prove your design against the real life. And when we talk about performance benchmarking, the things that we usually reason is those requests per second. And so about software system design, consider it as a scientific experiment. So you basically, it involves analyzing and documenting a lot of things, including requirements, outlining the architecture, detailed components definitions, and how they interact with each other. So this is more like input and output parameters of a scientific instrument. And the key elements of the software system design is architecture planning. So for instance, you can extract the components which should talk to each other. On this example, it's simplified schema of, let's say, user's proposal system and some mysterious facility. And basically then we can say, okay, we have users, we have a proposal service, and the users use the service, proposal service in terms use role-based access service to control the access and so on and so forth. And this actually defines the scenarios which your system will perform. And the next thing is component design. And this means specifying internal design and implementation of the component. Again, I prefer mind maps for documentation because I believe it's best in a compromise between the visualization and the text. And then you have, let's say, your component, and you decompose it into different aspects like functional requirement, non-functional requirements, quality attributes, which technology you will use to implement, and which APIs it will provide, and so on and so forth. And the last thing is to actually test and validate what you have designed. And here, where is this RPS come into play? So why request per second? Researching these metrics is important for 2 stages, so to say. So first one is capacity planning. So basically it says, okay, my node can serve, let's say, 1,000 RPS, so, and my estimate load is 600, so I'm good. And then it's also in runtime, it's a liveness metric. So for instance, again, if you designed 1,000 RPS, but the system gives you only 600, this definitely means there is some issue with either architecture, implementation, or anything. And to track those live metrics, so you usually use observability tools. So if you're interested how to, let's say, integrate observability tools with the SCADA systems, you can refer to this paper from the last Eclipse conference. And okay, just summarizing everything, here is a simplified systems design example. On the left-hand side, we have a node, which is client, and we consider some scenario. So basically, X clients do Y activities, and Y activities produces Z RPS. So multiplying everything, we get an A metric. And on the right-hand side, we have our node, which just runs our software, and it can stand up to, let's say, B RPS. And the goal of system design is to stick with the equation. So A less than B. So simple enough, right? And so how you actually get these numbers? For A, there is no magic. It's just some assumptions or predictions. Or if you have a running system, you can use observability tools. Here's an example from a scikit. When you go to the data sets, it actually produces thousands of requests, which gives you this RPS for that activity. And for the B, it's again no magic. It's just performance benchmarking. And the two most common scenarios for capturing RPS in the software is simulating I/O load or CPU load, because by the end of the day, this is basically what our software does. It's either waits for, like, say, backend response, database query, or file system response, and or it does some CPU, meaning, let's say, hash calculations or string manipulation, stuff like that. So I took this for popular nowadays text stacks to compare how they perform under different circumstances. So my, let's say, test case is typical virtual machine. We have a DAISY, which is 8 or 4 CPUs, 12 gigabytes of RAMs. And to simulate load, I use this VRK2 tool, which allows me to, let's say, specify how many clients do I have, how many connections do I open, for how long, and the most important is rate, which in my case is usually I tested some extreme values like 10,000. Normally you don't need to do that. And again, to actually simulate the stuff, there is no magic involved. You can just bring the whole system and make some load on it, but this approach I don't personally like, because then it's very vague in terms of what actually you are testing. So I prefer just isolate the problem, take, let's say, in this case, the technology stack, and simulate the I/O and CPU load with some corresponding mass or just sleep time. And here are some graphs. I don't want to go into much details here. I don't have that much time, unfortunately. But the idea is that, for instance, if I take a Node.js I/O load with like single instance versus 8 instances plus Nginx in front of it, and as we can see, the performance drops dramatically because higher is better. And with the CPU load, it's even worse, because Node.js is single-threaded, and we clearly see that on a single instance graph. It's like when we have 10 milliseconds, then we have just 100 requests per second, obviously, because at the time the CPU is busy. With pool, it was even worse. It couldn't handle higher load. And bonus slide here, I took that same technology stack, but removed the Express. I tested Node.js with Express framework. Then I tried without the framework, with just plain HTTP server provided by the Node.js, and the result was, on a single instance, 4 times better than with the framework. And it's clearly due to the framework doing a lot of strings manipulation to the route requests. And let's now switch to Rust. With CPU, it's more or less the same as with Node.js. CPU is very precious resource. If we consume it, we do not have a chance to serve anything else. With I/O, it's with a single instance not that interesting, but with let's say, pool of 4 instances and an Nginx in front of it, it could handle up to 10,000 requests per second easily, even with a very somewhat high load of 1 second. It was able to handle roughly 8.5 thousand requests per second. And I also member of DevHands.io community. So it's a community of let's say middle to CTO engineers, and from time to time we organize some boot camps, and I participated in this performance and scaling boot camp, and that means you not only can get a fancy certificate, but meet really great people who actually contributed also to this presentation by providing their results doing, let's say, Python Fast API. Of course, they had different use cases, so they tried different metrics, but I asked if the Python guy could, Kirill, provide, let's say, aligned with my metrics against the 10,000 requests per second, and Python showed somewhat 5.8 thousand requests per second, which makes it somewhat comparable to Node.js. And with Go, again, there was different metrics. I kind of extrapolated onto, let's say, 8 instances and Nginx in front of it, so it's performed somewhat similar to Rust. And as a bonus, I would recommend you this very interesting resource on the web. So they taken different web frameworks, run a performance tests, and then publish the result. And it's very detailed and rich on information. So, and I'm close to the end of my talk. Conclusions will be document everything, starting from assumptions and requirements, then architecture outlines, components and connectors diagrams, deployment diagrams. And if you are interested in how you can improve your documenting processes, there is a very nice poster in this conference dedicated to that one. And talking about the performance, so and the web applications, the rule of thumb would be that single instance won't stand even a moderate load. So probably the best would be to have at least 2 instances and a load balancer in front of it, which means that you have more components to manipulate with, and you will probably need some orchestration tool for that or solution. And if I would, let's say, start a new project now, especially on the back end, I would go definitely with Rust. And I hope, no. I prepared some fancy video. It's available on online. So basically here, a superhero guy was fighting with a bug because we are on the bugs conference. We need to fight with them. And that's it. Basically, thanks. And if you have any questions, yeah, again, and want to continue this discussion, please consider to connect on LinkedIn. Thank you.
You have to share it again. Question?
It's working.
It was right before. Who? Yes. No question?
Crystal clear.
Okay. They are getting tired, I think.
Yeah.
Okay, so let's thank Igor again.